This is a review of sections 10.1 and 10.2 that we talked about in class. 10.1 in our chapter on circles is about circles and circumference. On this first page, as you can see, I have listed definitions just in case you didn't pick up definitions in class today, so that you can pause the video and copy down anything that you need. I'm going to be talking about these definitions on the previous few slides to make sure that we have a picture of and an understanding of what the vocabulary is all about. But I wanted to go ahead and type these up for you and have them, because I sense that some of you did not get them in class when we were discussing today. Now we want to start, let's just draw us a circle here. We'll just get a nice circle. Oops. Well, I certainly don't want that one, do I? Let's try one that I can. Okay. So let's try one that's a little bit clearer for me. All right. There we have a circle. The red piece is the circumference of the circle. It's like the perimeter, the distance all the way around. The circle is the set of points equidistant from a given point called the center. And the center we're going to put in here with a little point. And we're going to call it C for center. You do not have to call it C. That's just the letter that I usually use. So to name this circle, I have circle C. That tells me that C must be the center of the circle. If I draw in a segment from the center, end point the center, end point on the circle, halfway across the circle, this is my radius of the circle. And if I double that radius so that I'm going all the way across the circle with end points on the circle, I have a diameter. The diameter is the longest chord of a circle, and a chord, by definition, is a segment with both end points on the circle. So I can have chords of all lengths in here. But my longest chord is my diameter. Okay? If I have a line that contains a chord, like so, here's the chord piece, but I have a line, I'll just call line L, or even a segment that contains a chord, that line is called a secant. And it's not the same secant we had in trigonometry. We also said that if we have a line in which all points are on the exterior of the circle, but one point intersects the circle, we have a tangent line. And that point of intersection is called the point of tangency. All right, when I started this discussion, I talked about the red piece being the circumference. Well, we have to know our formula for circumference. The circumference is pi times the diameter, or since the diameter is 2 times the radius, I could also use 2 pi r. Either of those formulas would suffice to find the circumference of the circle. We also talked about, in class, we talked about inscribed circles or inscribed polygons. So if I have a circle and I have a polygon inside, a many-angled figure from a triangle up to, a quadrilateral, a square, a pentagon, a hexagon, a dodecagon, however many sides I'm going to put in here. If I put in here a polygon such that every vertex of the polygon is on the circle, or I could say every side of the polygon is a chord of the circle, then I have this particular 1, 2, 3, 4, 5 pentagon is said to be inscribed in the circle. Again, every vertex is on the circle, every side is a chord of the circle. But my purple line, my circumference or my circle, in this situation, if I'm looking at the circle's perspective, the circle is circumscribed about the polygon. Okay? And one final vocabulary drawing I want to do for you from section 1. We're going to need another circle. And inside that one, we're going to need another, so whoops, it didn't want to go inside, did it? Inside, we're going to need another circle. When I have circles that share the same center point, like a bullseye, or my drawing here, or we said in class, like when you drop a pebble in a lake and the ripples come out from the same center point, then the circles that share a center are called concentric circles. We refer to your Spanish class where con or con means with and centric meaning center, so circles with the same center are concentric circles. Okay, I want to point out a couple of things that we talked about to set us up for exercises tonight. One thing we talked about that really comes later in the book in the discussion, but I wanted you to have it for tonight because I could see that you had some problems that you might question if we didn't mention this. I have my circle, and I'm going to put a diameter in my circle. There's my diameter. I have my center point in here. When I have an angle inscribed in a semicircle like this, which means that one side of the angle is going to go through the end point of the semicircle, and the other side of the angle is going to go through the other end of the semicircle. When I have an angle inscribed in a semicircle, which is half the circle, of course, then that angle will always be 90 degrees. That was one thing we needed to talk about today in class I want to review you on to help you do some of the exercises that I assigned for you. And one of the challenge problems had a drawing similar to the following. Okay, I'm going to have a circle, and this time my circle is inscribed in an equilateral triangle. So I want to come across here. I want to come up through, whoops. I want to come up through here. And then once again, down through here. Okay, this is, whoops, I'm sorry. What I'm looking at is the picture for number 53 on page 704. As you look at this, the information that we're given tells us that we have an 8-inch side over here. And that we have an equilateral triangle, so all sides are 8. One thing that we talked about was, here's my center point of my circle. When I bring the radius down to this point of tangency, we will have a right angle. That radius also bisects this side into a 4 and a 4. And we said when we pull this radius in here and extend it into the angle, I'm sorry, that looks kind of sloppy. Remember, since this is an equilateral triangle, it's equiangular. But this radius extends from the circle and goes into the angle down here, which is angle N. And it's going to bisect that 60 into 2 30s. So that's going to help you set up page 704, number 53. Do not run or panic because it's a challenge exercise. We want the circumference of circle P, and let's give that an exact circumference. Okay, just a little follow-up there from section 10.1. Now let's do a little follow-up from 10.2 so that those of you who are absent have a little something to look at, and those of you who had some questions in class can refer back and maybe fill in your gaps. All right, 10.2. is measuring angles and arcs. Okay, so I want to start by defining what is a central angle. A central angle. So we better draw another circle. We're going to be drawing a lot of circles over the next little bit. Well, I want to draw a circle. Okay, maybe this will do better. There we go. If I want to show you a central angle in my circle here, let me go ahead and put the center of my circle in here. And again, I'm a creature of habit. I'm going to call it circle C. So C is the center of my circle. But if I have an angle inside this circle, like so, and the vertex of my angle is the center of the circle, then I have what is called a central angle. So angle XCY is a central angle because its vertex C is the center of the circle. A central angle has as its vertex the center of the circle. And that angle, like all other angles, can be measured in degrees. And in this case, we're going to say, oh, this is about, we're just going to guesstimate, about 50 degrees. Okay, we're going to use that later. Now, look at the piece of the circle that lies between the two sides of the angle that we've drawn. That's going to be this piece of the circle that I'm highlighting. That piece of the circle is an arc, okay? So we're going to have here arc, X, Y is a piece of the circle, or piece of circumference. And in this case, again, it's XY. If I want to find the measure of arc XY, just like over here, I have the measure of angle XCY. The measure of a central angle is always equal to the value of the intercepted arc, or I can say the measure of an intercepted arc is equal in measure to the degree of the central angle. Now, XY is that intercepted arc because it's the piece it's the arc or the piece that angle is, as I said in class, biting off. It's like a Pac-Man biting out of the circle. So XY is my intercepted arc, and the measure of the intercepted arc is equal to the degree measure of the central angle. Now, I went a little bit further than that in class, which was really important, and told you that we're really going to look at assigning number values to an arc in two different ways. So if I've got arc XY, I've already said we can find the measure but we can also find the length. Now, they're not the same thing in this case. And so we want to make sure that we use the right terminology so we're all on the same page. The measure of the arc, when we refer to measure, we're going to be talking about degree measure. Which is equal to the central angle. But when I'm talking about the length, I'm talking about if I took a tape measure and I came here and I measured that. That's what we're calling the length of that circumference. So since a circle has so much beautiful symmetry and proportion in it, to find the length, there is a very reasonable proportion that I like to use. We say that the length that we're looking for, so in this case we're talking about the length of arc XY. That length is to the entire circumference, which is 2 pi r or pi d, as the central angle's measure is to the entire degree measure of the circle, which is 360. Okay, again, think about this and let it make sense. The length from X to Y, since it's a piece of the entire circumference, that piece has the same ratio in comparison to 2 pi r as the central angle does to the entire angles of the entire angles of a circle. Okay, so my length is to the circumference as my central angle is to 360. We talked about that a little bit today. Okay, and one little final piece I want to talk about. And this piece is not that terribly important. I just want to remind you that when you have arcs, again, pieces of the circumference, an arc whose measure is less than 180 degrees is considered a minor arc. If the arc measure is greater than 180 degrees, then I have a major arc. And we're going to talk about how to make sure we name those correctly. I'll just go ahead and slip this in here in your notes. These are named by the end points of the arc. But a major arc needs to be named by 3 points. Okay, so arc ABC, in which A and B are the end points of the arc, and angle B is a point on the arc between the end points. Again, I want to pick this up more Monday. Okay. Then we will have possibility of an arc measure equals 180, which means we have a semicircle. And to identify which half of the semicircle, we need to name a semicircle with 3 points. Okay, so again, we'll give that some more discussion on Monday. But I think that covers pretty much what we talked about today. So if you need to go back and review or have this in your notes, you'll be in pretty good shape.